Hi everybody, Captain Al speaking with your training tips designed to help make you a better, more knowledgeable flight simmer, pilot, or aviation enthusiast. Let's strap in and stow the HUD and see what is on the horizon for today. Our briefing is going to cover the all-important takeoff, in this case of the 747-8. The takeoff is designed to transition the jet from an awkward ground vehicle to a sleek air machine. The takeoff is designed so that thrust and lift can overcome drag and gravity, the four forces. The jet engines provide the thrust to increase the speed. As the speed increases, the wing or airfoil can then provide lift to overcome gravity and to get you airborne. We accomplish the takeoff by lining up on the center line. We do this by taxiing the aircraft from the gate to the active runway. Once cleared, we line up with the center line. We want to make sure the aircraft is perfectly lined up with the body gear steering not cocked off. And then we do a engine symmetrical power spool up to make sure the engines are symmetrical before we push toga. That will prevent any kind of asymmetric power application during the early parts of your takeoff roll. This is especially important so that any kind of yaw that would be encountered would be somewhat critical. Could be from an engine failure, could be from a contaminated runway, but prompt recognition and swift action would be required if the aircraft were to start to yaw during the initial parts of your takeoff roll. One of the things to prevent the asymmetric power application would to be symmetrical in your power application before you push toga. We advance the thrust levers manually, and then we ensure the engines are stabilized. For the Pratt engines, this would be 1.1 EPR. For the GE engines, for the 400, it would be 70% N1. And for the Dash 8, it would be 45% N1. Again, we'll be dealing primarily with the GE engines for the 400. The Pratt engines, the power would be a lot less of a power application than the GE engines. The GE engines will be much further up the thrust application on the primary ICAS, and we'll show you that in the virtual simulator. Once the engines are momentarily stabilized, we'll push toga. The thrust will advance to the takeoff thrust limit, whatever you set, whether it be TO, TO1, TO2, some sort of assumed temperature. And then we maintain centerline with rudder. And initially, the rudder will control the nose wheel steering at low speeds. But soon after you start to accelerate down the runway at about 40 to 60 knots, the rudder will become effective so that when you move the rudder pedals, you're actually controlling with the rudder as the speed increases. 65 knots, the auto throttle will go into hold. By 80 knots, the thrust should be set. The master caution and the beeper are inhibited at 80 knots. So any kind of caution that would occur, you'd get the alert message on ICAS, but you would not get the caution or the beeper. So something like a door that is ajar and causes a light to come on, you would hear no oral warning with that. And typically we'd continue the takeoff. V1 is your takeoff decision speed. Anything up to V1, we could reject the takeoff for an engine failure, engine fire, any fire, predictive wind shear, or in the captain's judgment, the jet would be unable to fly safely. A rejected takeoff prior to V1 in the high-speed regime would be any kind of loss of thrust, any kind of loss of control, or any oral warning that would occur. Any oral warning would be of the master warning variety, since the caution is inhibited at 80 knots. So any kind of oral warning above 80 knots would be something to reject the takeoff for. VR is your rotation speed. We normally rotate 3 to 5 knots prior to this speed. The rotation rate with all 4 engines operating is 2 to 2.5 degrees per second. It's a nice, smooth, continuous rate of rotation. Should take about 6 to 7 seconds to rotate by feel. And of course, this is not a mechanical maneuver. It's a feel maneuver as to what the proper rate of rotation is. The rate of rotation is important because too fast of a rate of rotation could cause a tail strike. The pitch should settle somewhere between 15 to 18 degrees, depending on weight. If you're heavy, about 15 degrees. If you're lighter, probably around 18 degrees. Usually no more than 20 degrees, even if you're light, would be sufficient once you are airborne. It's important to know that the tail clearance is not all that much on takeoff, and the proper rate of rotation is extremely important in terms of not getting any tail strikes. V2 is the takeoff safety speeds. With all 4 engines operating, that speed will be between V2 plus 10 to V2 plus 25. Generally, the flight director will command that speed. It depends on your rate of rotation as to where the speed will settle, but with all 4 engines operating, the speed should be somewhere between V2 plus 10 to V2 plus 25. If you rotate slow, then you're probably going to be more like V2 plus 25. If you rotate properly, you're going to be probably more like V2 plus 10 to V2 plus 15, somewhere in that range. It does depend how slow or fast you rotate to the takeoff climb attitude as to where the flight directors will settle to give you commands for that speed. On takeoff, VNAV is the pitch mode that is normally used on all takeoffs. Think of VNAV as an automatic mode. There are 2 types of climb profiles that most operators comply with, either ICAO-A or ICAO-B. ICAO-A is it's called the Noise Abatement Departure Procedure, or NADP-1. Used to be called ICAO-A. The NADP-1 procedure is more for noise abatement, and the NADP procedure 2 is more for if noise abatement were not quite a factor, and you could do kind of a distant community profile, then ICAO-B would be appropriate. Typically, probably more people use ICAO-A these days because airports are usually in more noise-sensitive areas. So probably in training, we do more NADP-2s or ICAO-B. And in reality, on the line, you do more NADP-1 procedures or ICAO-A procedures. The NADP-1, or used to be called the ICAO-A, is where the flap acceleration height is 3,000 feet AGL. The thrust reduction point is at 1,500 feet AGL. And the engine out acceleration height is at 1,000 feet, or whatever the airline SOP is, depending on performance charts and things like that. Some airlines will use 800 feet, some will use 1,000. 1,000 is more typical, but it really depends on the airline. And so at 1,500 feet above the ground, that's when the thrust will reduce from takeoff to climb. Again, depending on what you program, TO1 to climb 1, TO2 to climb 2, a D-rated takeoff thrust to a climb 1 thrust, or whatever's programmed. And then at 3,000 feet is where the aircraft will start accelerating to retract flaps. So the flight directors will give you commands for that if you're hand flying, or the autopilot will do it automatically if the autopilot is engaged. This is all programmed on the takeoff reference page. NADP-2 is, again, used to be known as ICAO-B. This is the Noise Abatement Departure Procedure 2, and this is more forgiving, if you will, for noise. If noise is not a factor, then the Flap acceleration height would be 1,000 feet. That's where we'd start nosing over for flap retraction for the speed to increase to retract the flaps. And then when we go to flaps 5, that would be the thrust reduction point where the thrust would reduce from takeoff to climb. And again, the engine out acceleration height would be whatever is the airline SOP, or 1,000 feet. Typically, I'll use 1,000 feet just as a standard, but again, some airlines will vary that depending on what their performance data shows. The NADP1, NADP2, they're programmed into the FMS CDU. They're entered on the takeoff reference page, as I said, during the CDU pre-flight. And again, you can enter as an altitude or a flap setting in the case of a thrust reduction point. For example, if you're doing an NADP1, you could enter, if you're using flap 10, you could enter 10-3000. Flap 10 would be the takeoff flap, 3000 would be the acceleration height. And then 1500 would be the thrust reduction point. Or we could enter something like 10/1000 for NADP2, and then put 5 for the thrust reduction point. And the computer would know that you mean flaps 5 and not 5 feet. So it would enter it as a flap setting instead of an altitude. So again, all fully customizable, if you will, on the takeoff reference page. For the takeoff, you can use LNAV VNAV if you were to fly a SID departure. This would be typical out of airports where you do have a SID assigned to you as part of the flight plan. And then, of course, if you arm LNAV and VNAV, LNAV will engage at 50 feet RA, VNAV will engage at 400 feet RA, and then VNAV will automatically comply with the profile that you have selected on the takeoff reference page in terms of your flap acceleration height, your engine out acceleration height if you were to lose an engine, and your thrust reduction point. Normally the pilot flying is on the takeoff reference page for takeoff, and the pilot monitoring is on the legs page for takeoff. If you're not using a SID departure, for example, if ATC were to give you a clearance to fly runway heading, maintain 5,000, expect vectors to XYZ waypoint, then in that case you're not flying a SID, so we would take off in toga. Once we're at 400 feet, we'd call for heading select. Heading select would be used as the roll mode instead of LNAV. And then, of course, at 400 feet, also VNAV would engage. And then you would go with the assigned profile as to what's on the takeoff reference page. If for whatever reason VNAV is not working, that's not normally the case. We normally do VNAV takeoffs 100% of the time. But if VNAV was not working for some reason, then we could use flight level change in terms of a pitch mode for takeoff. If we do use flight level change, then at the acceleration height, again, if that's NADP1, that would be at 3,000 feet, we'd select flight level change, and then we would bug up, rotate the selector to bug up to our clean speed. You can think of flight level change as a manual mode where you set the speed, whereas VNAV, when it was armed for takeoff, it was an automatic mode where it would increase the speed automatically when you get above the acceleration height. If we use flight level change for takeoff, then at the acceleration height, whether it be 1,000 feet or 3,000 feet, depending on NADP1 or NADP2, we would select flight level change and then bug up. And then at the thrust reduction point, we would push thrust on the MCP to manually change the thrust from takeoff to climb. That's going to do that, change the thrust from takeoff to climb manually, whereas in VNAV, it did it automatically when the flaps went to 5. In the case of NADP2, or when we reached 1,500 feet for the thrust reduction on NADP1. At the acceleration height, again, whether it's 3,000 or 1,000, depending on what you're doing, the jet will pitch the airplane down for flap retraction. As the speed increases, at the flap speed on the PFD, we'll retract the flaps to that setting, and we'll continue the flap retraction until the flaps are up. In VNAV, the speed will automatically go to the max flap speed limit, -5 knots, until you're clean. Again, in flight level change, you would have to increase the speed yourself, and then, of course, retract the flaps on schedule. When the flaps are up, the red boxes on the PFD will shoot up and disappear up to VMO, MMO. And at that time, we could bring the gear handle to off. The pilot monitoring would normally be the guy to do that, to depressurize the hydraulics. And then we do the after takeoff checklist is to make sure the gear handle's off and the flaps are up. You could look over and see that the flaps are up, but you'll notice usually on takeoff you're looking outside, you're looking at the PFD, and one real good indication that the flaps are up is when you see the red boxes, which are referencing the flap limit speed. When the flaps are up, they kind of shoot up because they're not referencing the flaps anymore, they're referencing VMO, MMO. So they'll kind of go out of view and disappearing, and that's when I can call for the after takeoff checklist. That's a technique in order to see that the flaps are up. Depending on weight in this airplane, the speed will be 250 knots or higher. You know, right around 630,000 pounds is where the speed will start to increase above 250 knots. I think at 630,000 pounds, you'd be about 252 or 253. And so as you get heavier than that, then the speed is going to increase. Now, most controllers know that these airplanes go long range. So heavyweight departures normally be flying at a faster speed, you know, depending on the weight, could be as high as 280 knots. So we'd have to advise ATC if we require more than 250 knots for operational necessity in order to maintain safe speeds at higher weights. And they will certainly approve us for that. They're aware of it, especially if a flight goes out the same time every day. They know that this flight is going out heavy and that they're going to need more than 250. So it's somewhat of a formality, but you still have to do it. You still have to let them know that you need that higher speed. The regulation is 250 below 10, but we can exceed that for operational necessity. And again, if you're completely heavy, it's going to be, that speed's going to be right up there around 280 knots when you're heavy. Okay, we're in the virtual simulator. I'm in the 747-8. This is my individual livery. It's for I manage my own funds. So the name of my hedge fund, personal hedge fund, is Alp Capital. And this is a shout out to Charles in Switzerland, who designed this for me. And it's a beautiful model that he designed. ALP are my initials. And you can see I have the Greek flag on there and the American flag on there because I'm Greek American. And it's just a great looking model, so thank you, Charles. Going inside, before I start on the takeoff, I released the fuel system shorts before this, and for those that didn't watch it, watch the fuel system if you choose to. Otherwise, since I'm in the Dash 8, I thought I'd go over the fuel system for the Dash 8 just in brief format here, just to show you some of the differences. Going to the overhead panel, move that synoptic over. And let me bring the cross feeds open and the overrides on. Some of the differences in the Dash 8, I'm not going to spend a lot of time on this, but the total fuel quantity is more in the Dash 8 than it is in the 747-400. In the 747-400 completely loaded, it's roughly about 383,000 pounds. In the Dash 8 it's about 406,000 pounds. There are no reserve tanks 2 and 3 in the Dash 8. There's a reserve tank 1 and a reserve tank 4 instead of reserves 2 and 3. Reserve 1 will feed into main tank 1 and reserve 4 will feed into main tank 4. The other significant difference, of course we're in the freighter, so there's no stabilizer tank. And the only real difference is, in order to figure out tank to engine, you have to really do something different than you do in the 400. And that is, you have to kind of add the main tank quantity to the reserve quantity and compare it with the main tank quantity. The same thing with engine 4. You have to add reserve 4 and main tank 4 and then compare it with main tank 3. And you can see in this case that if we add main tank 1 to reserve 1, what is that, about 44,200 kilograms, or 44.2. Well, actually we're in pounds, never mind. Since we're in pounds, that's going to be about 44.2 pounds. And main tank 2 is less than or equal to the total of reserve 1 plus main tank 1. And main tank 3 is less than or equal to the addition of reserve 4 plus main tank 4. And again, that's the same. It's 44.2. And main tank 3 is less than or equal to that. So you can see we are tank to engine at this time. If we go down to the primary ICAS, you'll see it is telling us we're tank to engine, and for takeoff we want to configure for that. So we'll come up and we do the same thing. We turn off overrides 2 and overrides 3, and then we close crossfeeds 1 and 4. And then the system's going to be happy we are tank to engine at that time. And you can see the ICAS message went away. So that's the only thing I'm going to mention on the fuel system. There's a few other differences. I mean, it has a nitrogen generation system for the center tank that prevents flammability, that operates at certain times, and maybe I'll do a segment on it at some point. But if you're interested in the fuel system, watch my presentation on the fuel for the 747-400. But I thought since I was here that I would show you the fuel synoptic for the Dash 8. Okay, we're ready for takeoff. You can see on the legs page that we have a SID departure. This is out of Minneapolis, and you'll see that we're going to fly a 301 heading for vectors, and then at some point we'd be given direct to Gopher, Golf Echo Papa, and then direct to Herbeck and Homer and Killebrew to cross at or above 14,000. We're cleared to 10,000, which we have on the mode control panel. So this is all programmed in the database, so it's going to be a SID departure. LNAV is armed, VNAV is armed, the flight directors are on. We've got blank, toga, FD, LNAV armed, VNAV armed, 8 degrees pitch up, basically ready to go. We've taken the runway. We've made sure the airplane is straight down the runway. The body gear steering is not cocked off. Again, there's no ICAS message here telling us that. If for some reason we did roll out and we didn't roll forward a little bit and the body gear steering were cocked off, the ICAS message would tell us that the body gear steering is not straight down the runway. So just to review a couple things that are going to happen as we take off. As we get to 65 knots, again, we'll advance the thrust levers manually to 45%. N1, we're in the dash 8. We'll let them stabilize, and then we'll push toga. The thrust will advance to TO2 thrust. That's what we have set for today. The airplane will start rolling down the runway. We'll keep the airplane straight, the longitudinal axis of the airplane straight down the runway center line with rudder. As the speed picks up, we'll transition from nose wheel steering to rudder control at about 40 to 60 knots. Once we get to 65 knots, we'll see thrust reference on the auto throttle, which would be right here. We'll see that change from thrust reference to throttle hold at 65 knots. And at that time, power will be removed from the servo motors. By 80 knots, we'll check that the power is set. As we accelerate down the runway, once we reach V1, we'll get an auto call out at V1. That's our takeoff decision speed. We continue the takeoff at that point. Once we reach our rotate speed, or slightly before, we'll start the rotation. Again, it'll be about a 2 to 2.5 degree rate of rotation up to our target pitch attitude, which is going to be right around somewhere between 15 and probably 17 degrees. We'll transition to the flight director at that time. With a positive rate, we'll get the gear up. And then LNAV will engage at 50 feet. VNAV will engage at 400 feet. We've got NADP1 programmed in the takeoff reference page. So as a result, we'll get a thrust reduction from TO2 to climb to at 1,500 feet. And then at 3,000 feet above the ground, the airplane will start to accelerate for flap retraction, and then as we increase the speed, we'll get to our flap speed and we'll retract the flaps on schedule. Once the flaps are up, in this airplane, the Dash 8, there's no need to bring the gear handle to off. The gear handle stays up, it automatically depressurizes, and so this is very similar to a 777 or a 787, where it's a smaller gear handle. And unlike the older 747-400, we don't have to depressurize the hydraulics manually by bringing the gear handle to off. It does it automatically. So with that, I'm going to add the power to 45% N1, which is probably right about there. We'll let the engine stabilize. We'll push toga. We see thrust reference. We'll keep the airplane straight with nose wheel. As we get to 40 to 60 knots where we are right now, the rudder will start to become effective. 65 knots, you'll notice we go into hold.
80 knots.
80 knots, the power is set. We continue to accelerate. Add a little bit of rudder here just to keep the center line. As we approach V1, we're more likely to continue. At or above V1, we will continue the takeoff. Here comes V1. And here comes our rotate speed. We'll start to rotate, nice, smooth, continuous rate of rotation at 2.5 degrees per second. We'll get the gear up with a positive rate. And our speed should settle somewhere between V2 plus 10 and V2 plus 25. You can see we're right about there at V2 plus 10. And now it's re-referenced to our current speed. Now you'll notice that the airplane's not accelerating because we have NADP1 selected on our takeoff reference page. I'm continuing to hand fly the airplane here, so it's you can see it's FD, it's not command. 1,500 feet, we should see the thrust reduce from climb to, actually I already did it, from takeoff to climb to. Once we get about 3,000 feet above the ground, the airplane will start to accelerate. I didn't point out, but LNAV engaged at 50 feet, VNAV engaged at 400 feet. Really didn't do anything at 400 feet until you get to the thrust reduction point, and then it would reduce the thrust. And then at 3,000 feet, it will start to accelerate us for flap retraction. Minneapolis is like 840 feet, so right around 3840 or so, we'll see that speed bug go up and start to accelerate us for flap retraction. There it goes. We're 3,000 feet above the ground now. Lower the nose. To stay in the flight director, the airspeed starts to accelerate. And then we'll retract the flaps on schedule. So as long as we're accelerating and we get to our flap 5 bug, we can go to flap 5. So right in here we'll go flaps 5. Continuing to pitch down, adding a little bit of trim. And again, this would be your standard takeoff using VNAV. And in this case we are using LNAV also because we have a SID departure. And if ATC gave us a runway heading, we would have went to heading select at 400 feet. Went to flaps 1. There's our bug for flap up. Notice the red boxes coming into view on the speed indication. There's flaps up. And now watch those red boxes as the flaps come up. Those red boxes will disappear. See how they're going up? And they're out of view, and usually at that point the flaps are completely up. Actually in the Dash 8 they weren't quite. They weren't quite up. But normally when the boxes disappear, the flaps will be up. And at that point, nothing to do in the Dash 8 because we don't have to bring the gear handle to off. So as we come down back into the flight deck, you can see again this on the Dash 8 you have the smaller gear handle. It stays up, doesn't come off. There is no off position. And so then we can complete the after takeoff checklist. So that completes the takeoff briefing. After you do take off, you have the option of either hand flying the airplane or getting on the autopilot. For the Dash 8, the autopilot can be engaged anytime above 200 feet. For the 747-8, the minimum autopilot engagement altitude is 250 feet. In the U.S., you'll find most pilots will fly the airplane normally at least through 10,000 feet. Some will fly it higher, some will get on the autopilot lower, but generally in the U.S. people tend to want to hand fly at least some of the departure until they get to more of an en route phase and then get on the autopilot. This does a couple things. It maintains proficiency, hand proficiency. In other countries, airlines may tell their pilots to get on the autopilot at the minimum autopilot engagement altitude, and they don't want them hand flying the airplane above that. The advantage to that is it does reduce pilot workload But generally, we put in the U.S. we put some high value on maintaining proficiency, since these airplanes, you really don't get a lot of hand flying time other than the takeoff, the departure, some of the arrival, and the approach and landing. Probably not even the arrival, more like the approach and landing. And normally it gets busy during that phase, so normally the autopilot's coming off at maybe 1,000 feet, 1,500 feet, something like that, in order to gain some proficiency in approach and landing operations. So because these airplanes aren't flown around with hand flying them all the time, pilots tend to want to hand fly. So again, that completes the takeoff briefing, and thanks for watching. Okay, let's lower the HUD and go flying. Until our next briefing, keep the blue side up. Captain Al, out.